welcome to my YouTube channel. Thanks for 5,000 subscribers. I really appreciate that. We can put more effort by sharing this channel to those who actually need them. Thank you very much. I really appreciate it. Do well to subscribe if you are new here, and if you are old here, thanks for coming back again. So we want to look at the WAEC 2023 Physics Practical Mechanics. Actually, I've posted a video on this before, but looking at the setup of that particular video and the apparatus, it seems not to be feasible. And then the experiment, actually, due to some factors, those things seems not to work together. So I just have to cook another thing to make sure that at least it gets to your satisfaction, and then you would be able to use it effectively. So now we are going to look at the setup for the experiment. Now let's look at this diagram. This is a Retort stand, this is an helical spring, and this is a meter rule, and we have a mass marked P, and at the same time we have a mass marked Q. We are going to use that as we proceed on the experiment. So this is mass M, of which we are going to vary when taking readings, why this one will be constant all through the reading when we take them, why we exchange it with Q again and repeat the procedure. Then we have the knife edge K. So the apparatus is going to be set up this way, and then we are going to follow up due procedures to solve them. Let's look at the procedures as follows. You are provided with a meter rule, Retort stand, knife edge, and stopwatch and other necessary materials. Those are what we're going to use. Okay, we're going to measure and record the center of gravity G of the meter rule. So we are measuring the center of gravity G of the meter rule at first and record that at the top of the table. Now, the next thing is to set up the apparatus as shown above, hanging mass P as G. So we are going to set up this apparatus and hang the mass P at the center of gravity using a thread or string. And at the same time, we're going to make this also and hang all these with strings. Now, the next is we're told to hang mass M equals 40 grams at A. Look at point A here, which is 10 centimeters away from the end of the meter rule. Okay. Then after hanging that, then we have to tap the meter rule. Okay, let me make us see that. Okay, we are meant to tap the meter rule to oscillate vertically. So which means the string oscillates this way. We are going to tap it this way so that it can oscillate vertically. So then thereafter, we determine the time taken for 10 complete oscillations. Then we repeat the procedure by changing the mass M to 50, 60, 70, and 80. So afterwards, the next is repeat the procedure for the following masses. So in each case, we are meant to determine the time taken for 10 complete oscillations. So we call that time P. So now let's proceed to the next step when we look at hanging mass of Q. So we are before we do that, we have to evaluate the period. So we are meant to evaluate the period when P is hung at the center of gravity using time taken for 10 complete oscillation as P is being hung there over number of oscillation. Then we repeat all procedures with the replacement of P with Q. Then thereafter we evaluate TQ as well at the same time. Then after that we need to evaluate T equals TP minus TQ. Then also evaluate T squared. Then after that we plot graph of T squared against M. Then determine the slope S on the graph and the intercept C on the vertical axis. Then after that we are meant to calculate K, which is the spring constant or force constant, equals what? 6,400S, that is the slope, over 4 pi squared. So now let us look at the setup, how we can achieve this diagram. How we can achieve this diagram of setup and how the experiment will go now. Okay, in the twinkling of an eye, let's see how we can do that. Okay, according to the first procedure, we are told to find the center of gravity of the meter rule. So we balance it on the knife edge. So let's try to do that now. Now the meter rule has balanced at okay, exactly 50 now. It has balanced at 50. Are we seeing that? So we have determined the center of gravity. You can see it's actually balanced at 50. At point 50, yeah, that is where it balanced. So now the next thing is for us to go for the other procedure. Now, the procedure is to arrange the apparatus as shown here. So now let's arrange it. So we are going to look at the arrangement to bring the camera around the arrangement. The meter rule is going to be placed on the knife edge 5 cm away from this end. So let's place it on 5. So then thereafter we hang the other end of the meter, which is also placed 5 cm to the spring. So let's achieve this. So the setup goes this way. We put this at 5 cm mark points on the meter rule, that is 5 cm. Then this is placed at 50. Then this at 90. Why this placed at 95, which is 5 cm equal. Then you can see the spring hang on the Retort stand. So now we have to proceed on the experiment. How do we go about it? So let's look at how we can perform that. So now we are going to hang a mass of 40 grams, which is here already. Then after that we tap this in this manner, or probably this manner, for it to oscillate, and we are going to count the time taken for 10 complete oscillation. So, and mind you, when you're taking your oscillation, when you tap this way, this is the point where you release it. So you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is how to count it. So now let's count by owning the stopwatch. So now let's take the 10 complete oscillation while we tap this in this direction and see. Now I'm holding the stopwatch, endeavor this is around 5, so, and it doesn't leave that 5. So now let's go. 1, 2, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the value is 14.47. 14.47. And don't forget, the value should be recorded in 2 decimal place. It should be recorded in 2 decimal place. So now the next is to add 50. And how do I make 50? I'm going to add 10 to what I have here. Okay, or I have a 50 direct, so I can actually remove this. I can remove this. Okay, I have a 50 direct here. So let's remove this. Okay, this is 50 on its own. So let's remove this, and this is 40. So I'll put 50. So now let's take the oscillation again. Let's take the oscillation again for 50. Okay? Are we on the stopwatch now? Let's go. 1, 2, go. 1, 2, 3, 4, 5, 6. Okay, I don't want that. Let's take another one. Sorry. Okay, now let's go. 1, 2, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 14.52. 14.52. So now that's 50. Let us add 10 to 50 to make it 60. So this is 10. This is 10 grams. So let's add it now to make it 60. So I've added 10 grams to make it 60. 14.52. Now let's go again. So we have 1, 2, 3. Okay, I don't want that. Let's go again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 15.39. 15.39. So let's take that. Then now the next is to add 70. So I can add 10 gram mass to that to make it 70, or probably I remove 10 gram, the two 10 grams, and then add just 120 grams to it to make that 70. That's from 50 now. So then, now let's take the solution again. Okay, endeavor this does not go away from 5. So let's go now. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 15.79. 15.79 for the 70. 15.79. So now let's take for 80, which is the last one. So to this 70, I just need to add 10 to make it 80. I just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 17.0. 17.0. 17.00. Actually 16.9 whatever, but let's make it 17.0. Okay, maybe little error might occur after that. So now the next thing is, let us remove this. Let's remove this. Then go back to, we have to remove and replace with Q. We have to remove and replace with Q. So this is 40. We return the 40 back into place. Let's keep the 40 back in place. So this is 40. Then I will have to remove this and introduce mass Q. This is mass P now. Let me remove this and return mass Q there. Okay. So this is mass P that has been removed. So let's put back mass Q at the point G, center of gravity. So and that's this. It's done already. So let's balance it up again, all once again. So let's take the oscillation. Let's take the oscillation. So we have 1, 2, go. Okay, sorry. Now let's go. 1, 2, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 13.53. Let us look at hanging it to be 50. So what would have happened at 50? So at 50, what are we going to have? So let's hang mass 50. So now let's go again. The oscillation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 14.29. 14.29. So we go for 60 by adding 10 to 50. So now let's go for the oscillation. Now 1, 2, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 15.2. Okay, let's go for 70 now. For 70 gram, which has been hung already. So now let's take the oscillation for 70. So now let's take the oscillation for 70 grams. So 1, 2, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 15.54, that is the resolution we take for this. So now let's look at, can you see the trend of increase? That's 70. Okay, let me just add 10 to that to make it 80. So let's add 10 to that to make it 80. So now let's take the resolution once again. Right there. 1, 2, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 15.95. So we have 15.95 as the reading. So now let's go to the table and make our table and then plot graph and see the results. Okay, now we are done with the experiment. Let us now input the values into the table. So if I divide this to calculate TQ, I will have to, okay, this is actually TP, not TQ, so then this is TQ. So to find TP, we have to just divide all these by number of oscillation, which is 10, so this will be 1.447, let this be in 3 decimal place, then this will be 1.452, this will be 1.539, and this will be 1.579, and this will actually be 1.700. Okay, then we go for these two. This will also be 1.353, this will be 1.429, this will be 1.520, this will be 1.554, and this will be 1.595. So that is that and that. So now the next thing is to evaluate T equals TP minus TQ. So now to evaluate this is just quite simple. So I will subtract the value here from the value here. So I'll be having 1.447 minus 1.353. So that gives me 0. Now, as we can see the values of T squared there on the board, we have 8.836 times 10 raised to the power minus 3, and we have 0.529 times 10 raised to the power minus 3. I just have to make all these uniform with 10 raised to the power minus 3. So now the next thing is to go and plot our graph and see how it looks like. Okay, now let's go and do that now. So this is our table of value. On top of this table of value, you record your G, which is what? 50 centimeter, 50.0. So then now let's plot the graph. So now to choose a scale on the graph is very important. So since we are plotting T squared on vertical axis, the scale on vertical axis should be well placed. Then plotting M on horizontal axis is very simple. So that is going to be what? We can actually take 2 centimeters to represent 20, and that will be quite easy. So if we take 2 centimeters to represent 20, from the origin here, we can have 10, 20, 40, 60, 80. That will be very short. So we have to take 2 centimeters to 10. So because we have to cover at least 70% of the graph book. So we have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So we can actually take this. Is okay. So let me put my line on the origin. So okay, let's see how the graph is being plotted. So I am placing this here, down here. So which means I have to write my unit, that is M in gram at this point. Then from here I will be having my 10.00, let that be in 2 decimal place, 20.00, 30.00, 40.00, 50.00, 60.00, 70.00, 80.00, then 90.00, then lastly we have 100.00. So that is the M axis or horizontal axis. Then on the vertical axis, all have to be times 10 raised to the power minus 3. So the scale, whatever scale we are choosing, we have to multiply the resulting scale by 10 raised to the power minus 3 as it is in the table. So on the vertical axis, each scale we are using for 2 centimeters, we are meant to multiply the value by times 10 raised to the power minus 3. So which means in the unit side, I'm going to put that is second squared, so I will put times 10 raised to the power minus 3 second squared. So this is how it seems to look like. Let's see it's there. So I will have to put times 10 raised to the power minus 3. So let's look at it very well. Times 10 raised to the power minus 3 second squared. That is how it is. So then I can choose a scale to meet up with others. So now what next? I have a value ranging from 0.36 to 11. So I can actually choose a scale that will accommodate all this. So then if I choose a scale that is 2 centimeter to 1 unit, if I take 2 centimeter to 1, then I'll be having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't forget, each one represents times 10 raised to the power minus 3. So if 2 centimeter represents 1 unit, from here down here will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I will have 11 here. So this is from 0 here to here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Anyway, let's take it that way. Okay, I will have 0 here. So then here will be 1.00. Then here we have 2.00, 3.00, 4.00, 5.00, 6.00, 7.00, then 8.00, then 9.00, then we have 10.00, then also 11.00. Then lastly we have 12.00 up there. So now this is it. So we have to state our scale. So the scale used on t squared axis. On t squared axis, a scale of 2 centimeter to 1 times 10 raised to the power minus 3 second squared is used. So this is the scale on t squared axis. So then on m axis, we have a scale of 2 centimeter to 10 gram. So now that is it. So which means each line under the 2 centimeter represents 0.1, if that is the case. So we can actually get 0.6, 0.3 and all that values on the graph. So it is now easier for us to plot it. So now let us go ahead to pick up those values on the graph. So now at point 40 on the table, when m is 40, what is the value of t squared? I have 8.836. So I'm actually taking 8.8. Don't forget all is times 10 raised to the power minus 3. So now we go for 8. So each line here represents 0.1. So if this line, thick line, represents 8, then here will be 8.1, 8.2, 8.3, 8.4, 8.5, 8.6, 8.7, 8.8. Quite easy. Then I can raise it up a little bit, but let's just approximate to 8.8. So 8.8 goes to 40. This is 10. Okay. This is 20. This is 30. And this is 40. So it goes this way. So 8.8 goes to 40. We have done that already at this marked point. So now the next thing is to go for the next one. That is 50 goes for 0.529. So let's say 0.53. So now let's go for 50 to 0.529. So that's 50 goes for 0.5. So 0.5 will find its way around here. So that is 0.1, 2, 3, 4. So this 0, 0.1, 0.2, 0.3, 0.4, 0.5. So that goes to 50. So I've marked that point. Now the next is to go for 60 goes for 0.36, or let's say 0.4. Okay, we can make that in the table 0.360 in 3 decimal places. So we have 60 goes for 0.4, so this is 60, 0.1, 0.2, 0.3, 0.4. Okay, that is it. Now what next? Let's take 70 to 0.625. 70, this is 0.5, so 0.6 before somewhere here, 0.625 for somewhere here. So that's it. Then lastly, we take the value of 80 to 11.05. So 80 goes for 11 and 11.025. So let's actually take that to be 11. Now this is great. Look at how our graph seems to look like. Okay, looking at it very well, if I take the line here, it's going to give me a negative slope this way, but if I take these two, it's going to give me a positive slope. So let me go with the positive slope and take this, and definitely there will be intercept on y-axis, since we are told to find intercept on y-axis. So I'll prefer to take these 2 points. So these 2 points is now the best fit line for me. So I have actually drawn the best fit line now. See the best fit line, the way it shows. Then the next thing is to read my intercept C. My intercept C falls at 6.1, 2, 3, 4, 5, almost 6.6. So we are going to have 6.65. Okay, let's take 6.1, 2, 3, 4, 5. Okay, 6.59. So intercept C is equals to 6.59. That's the intercept on y-axis. So now let's take the slope of the graph. So how do we determine the slope of the graph? The positive slope of the graph now, because other values we tend to give a negative slope. So now let's take the positive slope of the graph and see what goes on. So now I'm taking that from the readable value. So let me take that from 80. Alright, 80 down to, I'm taking that from 80 down to 40. On the vertical axis. Okay, that will not be enough, so I can't take up to that. So let me just take it to 0.70. Okay, to 0.70. Okay, now let's look at the slope. So forget about this line, just focus on this. So this is change in t squared, while this is change in m. So the slope s will be calculated soon. Change in s, that's the slope s, is going to be what? Change in t squared over change in m, as it is. So now let's go ahead to calculate the slope of the graph. The slope is change in t squared over change in m. So let's read the change. From the vertical axis, we have 11 minus 7. So don't forget, each will be multiplied by times 10 raised to the power minus 3. So that will be what? 11 times 10 raised to the power minus 3 subtracted from 7 times 10 raised to the power minus 3. Then this all over change in m. So let's look at m. So I have a value on m here to be 80, and here I'll be having 8 gram. So that is 80 minus 8 gram. So let's calculate that and see what we have. Okay, the value of the slope is going to be calculated now. The change in t squared is 4 times 10 raised to the power minus 3, and the change in m is 72. So if I'm to divide that now, 4 times 10 raised to the power minus 3. So the answer divided by 72 is going to give me 5.556 times 10 raised to the power minus 5. So slope s is 5.556 0.56 times 10 raised to power minus 5. Now, what is the unit of the slope? Don't forget, change in t squared is second square per gram. So this is the unit of the slope, second squared per gram. So now, the next thing we are meant to do is we have recorded the intercept C to be 6.59. Then after that, we are meant to calculate K, which is equals to 6,400 S over 4 pi squared. So now, to do that, I have 6,400 times 5.556 times 10 raised to the power minus 5. This all over 4 into brackets, pi is 3.142 all squared. So then what next? Let's just make that easier. So I have 5.556 times 10 raised to power minus 5. Then if I multiply that by 6,400, I think I have K equals 0.3556 in 4 decimal place. Then the pi squared, which is 3.142 squared, multiplied by 4 gives me a value 39.4887. So now, dividing these two values, we have calculated. Dividing these two values, we're going to have 0.3556 divided by 39.4887. So that gives 9.005 times 10 raised to the power minus 3. So K equals 9.005 times 10 raised to the power minus 3. Then what is the unit of K? The unit of K is going to be the unit of the slope, which is sec square per gram. Sec square per gram, because all the values here are constant. So that is that on the experiment, and anticipate for the rest of the part of the experiment. What are the precautions that you need to take in order to obtain accurate results? Okay, the precautions are: you need to avoid parallax error when making use of the meter rule. Then you need to ensure that the stopwatch is stopped immediately the 10 oscillations are complete. Then more other precautions include ensuring that the knife edge is in position of which as directed in the question. The position does not change while the system oscillates. So thanks for watching this video. Please subscribe to the YouTube channel and endeavor to share the video as well. Thank you.